Okay, so it's time to continue. Our next speaker is Diego Rubira Garcia, who is going to tell about, well, he's a friend of mine from too many years. Too many.
This is time.
It's time to break this relation. Okay, so he's going to give the first lecture on the ray tracing code that we are promoting in this workshop. And well, he's a professor at the Complutense University of Madrid, and he's participating in this workshop to speak about compact objects and the characterization of their physical properties via the optical aspects, no? The emission from accretion disks around these objects. So, Diego, you can start whenever you want.
Okay, thank you very much for coming. So, good morning, everybody. So I'm happy to be the first opening fire about these 3 sessions that we are going to talk about how to produce images of black holes and other compact objects using the physics of accretion disks. So today, I'm in charge of today of talking to you about the analytical aspects. Okay, so I'm going to explain you the background equations, the background geometries, the main ideas behind this field of research that, as you may be aware of, is becoming very popular because we have data about these things. So we have a great opportunity to do gravitational physics and to test compact objects using this new window that appear into the universe. So we are theoretical physicists, so this is our focus. So we wanted to test new objects, to test the strong field regime or gravitational interaction using this tool. We have been learning from scratch about how to do this since maybe 3 years ago, maybe. So we knew nothing about this thing. And so learning from there, we have elaborated from nothing to what we are doing now, which is produce images, produce physics, in the end publish papers. Okay, so this has been very productive to us, and since we have working codes based on Mathematica that everybody can use, because for those of you that have been using Mathematica for some time, so this is very easy to use, and amazingly, even it's not that so popular as other things like Fortran or Python or these things. So it's very flexible and it allows you to do many things. So even for us, we have been doing this on only 3 years. So we have been able to do a lot of things with it, a lot of things to come. So we are welcome to share with you our knowledge, and more importantly, to those of you that are listening to this talk and to this video, to provide you with the notebooks. Okay, so you will be able to use these notebooks for your own research, to adapt them to your own purposes. And my goal today is to explain you not the codes, which this is the duty of Gonzalo Olmo and Joao Rosa, that are going to talk after me. I'm going to explain you the analytic things. Okay, so the main equations and the main ideas. Because as you are going to see, the equations are quite simple as compared, for instance, to other competitor field, which would be gravitational waves, to do the same thing with other source of information. Here, things are very simple from a mathematical point of view. But as you are going to see, things get messy very quickly because of several problems that we are going to find. And these problems pervade the whole field, and it's preventing us to extract information about compact objects and the gravitational interaction itself. So I'm going to try to explain you the basic context and how they are entangled, how they are putting a lot of difficulties in the field. Okay, for everybody working on it. Okay, so this is the rationale what I'm going to tell you today, and the basis for the talks that are going to follow about the notebooks. Okay, so our code is already available in the Mathematica webpage because we requested this. We were requested this from the company, and so we thought it was a good opportunity to share this knowledge. Okay, the code is already out, so out of our control, so you can clear the access, and so we are going to see how it works. Okay, that's not me, but the true expert. Okay. I also must mention that the code was an invention of Gonzalo, again from scratch, nothing present there. So from the first line of the code until the very end, but was further elaborated by myself, and then Joao Rosa joined us to implement his own version. Okay, so actually we have several versions of the code depending on what exact object or what exact feature you are interested in investigating. Okay, so it's very flexible to adapt it to your own purposes. Okay, so this is the idea. Usually it's a word. What do we think? No. Okay. No. Okay. No. So this is for 5 parts talk, talking about different problems that we find. Hopefully it won't last for 1 hour and a half, but I will do my best to summarize. Okay. So first the challenge. What do we want to do? Okay. So we have data about what? About these 2 things that should be familiar to all of you as physicists. So this is very popular. These are the 2 images of the N87 galaxy and our own galaxy, the Milky Way, or the object. There is a star at the center of the Milky Way. Okay. So these 2 objects are optical images of what of the matter that is surrounding these 2 objects that lie at the heart of our own galaxies that are identified as supermassive objects, canonically identified as supermassive black holes. And so this material that is surrounding the object is heated and the process operating, and it's light. And this electromagnetic radiation, and this electromagnetic radiation illuminates the object that is behind, and part of this radiation is able to get to us and produces this image. Okay, so without knowing anything about what is happening here, so you see 2 main features in this image. So there is some kind of disk, illuminated disk, surrounding something in the middle which is dark. Okay, this field is usually popularly known as shadows, because by shadow they usually refer to the dark central area, while the region around, which is illuminated, is the photon, is called usually the photon ray. Now, these 2 concepts are a little bit tricky, a little bit subtle, so I'm going to try to explain it in more detail. Okay, the word shadow is usually employed in a very loose way, so sometimes it's not even defined what is exactly, but somewhat is related to the dark centrally. And the photon ring is the luminous ring that surrounds the object. Okay, why is this important? Because these images, or the main features of these images, as I'm going to explain, are generated or are originated around what is called the photon sphere of the black hole. And for instance, in the case of a spherically symmetric black hole, the Schwarzschild solution, where the event horizon is located at 2m, 2 times the mass of the object, the photon sphere is located at 3 times the mass of the object. So it's very close to the horizon. Okay, so because of this, we are dealing in the strong field regime of the gravitational interaction, or we can have access to that. Okay, so this field allows you to go beyond the weak field limit test that we have been doing for decades on the nature of black holes, and together with gravitational waves. So it's taking place within what is called nowadays the multi-messenger astronomy. So the testing of objects, or astrophysical objects with several means: neutrinos, magnetic radiation, gravitational waves, all these things. Yes.
Do you want any questions?
Yeah.
Okay. So when you say strong field regime, these objects are extremely. So I
would that's another thing. That's another thing. If the object is extremely massive, so it's not a strong field regime.
Okay.
Because that's what we have access now. But technology is improving, I'm going to explain, so we don't know exactly what we are going to have access in the future.
Okay, so smaller black holes might be also photographed. So
yeah. That's another thing. That's another thing. If the object is a string or a okay. So that's the thing. So in principle, like with gravitational waves, that actually that's not the topic of my talk, but gravitational waves are originated like the same surface that we do with sounds. So they happen at the same place. Okay. So we have two means of testing the same thing. The difference is that nowadays we use gravitational waves to test black hole astrophysical size black holes. And we have SAGOs for supermassive black holes. Okay. So analysis of the photosphere takes you to two different phenomena, into different things. Okay. And since we don't know what we are going to be able to measure in the future, so we have a new tool to study our theories of gravitational interaction. Okay. So getting into the details of this image, this image agrees mostly with what we were expecting to have. Okay. This is in agreement with the results of what is called magnetic dynamic simulations within general relativity. Okay, so this is the field what is called GRNHT, which basically means that you take the Einstein equations, tackle them numerically, and on the matter field side, you need to model the accretion disk. This modeling is extremely complex. It's difficult to do. Typically, you need to introduce a lot of assumptions about the behavior of the accretion flow, and this problem is typically treated as if it were a kind of fluid with several additional ingredients. That's what is called magnetic dynamic simulation. Okay, so this belongs to the field of numerical relativity, which is something very well developed in the literature, and particularly within the Spanish community, and particularly within this university, which is pioneer in this sense. Okay. It also has the word of general relativity, general relativistic, because it assumes by default the framework of general relativity. Also, from a conceptual point of view, in the sense that we are going to study the objects held by general relativity and only general relativity, and also because it applies the techniques of numerical relativity for general relativity or Einstein field equations. So you can imagine, if you move away from general relativity to any other theory of gravity, you have to start anew with the simulations. Okay, there is very little done. That's a big problem. That's another big problem also with gravitational waves. Okay. In any case, when you do theoretical analysis and compare with simulations, you get to the same conclusions. There are two main features that you are expecting in your images. First, there is something which is called in the image photon ring, which is highly correlated with a theoretical feature that appears around the object, which is called the photosphere. There are two different things. One is the thing that surrounds the black hole, which is the photosphere, the photon cell when the black hole is rotating. And the photon ring is something related to what you have in your screen. There are two different things. Okay. So the photon ring is something that closely tracks what is called the critical curve. It's the projection of the photosphere on your screen is called the critical curve. And this critical curve is correlated with the photon rings, because there can be more than one. There is only one critical curve, which is the projection of the photosphere in your screen. But the photon ring, which is the actual ring that you observe, can be decomposed in more than one. Okay, so there are three different things. Photosphere is the surface of unstable bound geodesics around a black hole, 3M, because of Schwarz, which deformates into a cell, which is called the photon cell when the black hole is rotating. Okay. Then this photon sphere mathematically is projected in your screen in something which is called the critical curve. And the third thing is the photon ring, which is related to both, but is not exactly assimilated to any of them. Okay. That's the first difficulty that we find. Okay. Now, the second feature that you find is that the dark central area. This is usually called the saddle. Though a more careful, a more conservative word used in papers is the central brightness depression, which might consider on the saddle or not. Okay, it's a different thing. Central brightness depression is the dark central area. Whether this coincides with the saddle, and I'm going to explain what is exactly mathematical term with the saddle or not, depends on other ingredients related to the accretion disk. For instance, in this image, which is the numerical image, when you run your Einstein equations numerically, solve them, you have something here which is called the photon ring, which is the actual luminosity that you see around your object. Central to it, there is some dark central area, and there is something here which is called shadow. And there is another word added, which is inner shadow, which is a different thing. Okay, I'm also going to explain. So with the shadow, you have another 3 different words: brightness, depression, shadow, and inner shadow. There are 3 different things. These 3 different things we consider normal, depending again on the accretion disk. As I'm going to explain you, is typically the biggest problem that we have when we try to get images of these objects. Okay. So this image, this simulation is taken from this paper, and this is the image that you observe. The fact that it's blurred here is because the resolution is finite. We are not able yet with current instrumentation to get the final details of this image, which is the same, because the devil is in the details, as I said, and here the details is where we find the choices of potential neophysics, or whether we can confirm that our physics based in general relativity is correct. Okay, but technology always keeps progressing. So at some point in the future, probably in the near future, this image is going to be better resolved. So we have an opportunity to connect these, which are the simulations, with this, which is the image. Okay. Okay, so let us think on general relativity. General relativity, there is a single black hole, which is current. This comes from a number of theorems. Okay, on the uniqueness and no-hair conjecture. So these are theorems from the 60s telling you that there is only one type of black hole in the universe, characterized by mass and rotation, also by charge. But charge is typically neglected in astrophysical environments, so it plays no role here, or it plays a very secondary role. Okay, so we can disregard it as a first approach.
Sorry, what do you mean? What about Schwarzschild?
See?
What about Schwarzschild solution?
The Schwarzschild solution is when there is no rotation. But typically, astrophysical black holes rotate. Okay?
It's just a particular.
It's a particular case. Okay? So in practical terms, rotation influences the properties of the black hole in a slight way. Actually, as I'm going to tell you, or can advance you, the uncertainties in the behavior of the disk are much larger than the effects of considering rotation. So as a very good first approximation, you can neglect rotation. From a theoretical Cartesian point of view, astrophysicists are different species. Okay, they care about different stuff than us. Okay. What is the problem? Why we don't go for rotation? Because rotation, from a theoretical numerical point of view, complicates the game and extremely difficult. So in order to gain a little knowledge of what is happening, you lose everything that you have in the spherical simulation. So I'm going not to talk, and neither me, neither them, or about rotation at any place of this talk, rather than connecting with observations. But our notebooks do not deal with rotation. That's an important thing that you incorporate later in the game. But we are not worried about this state because we have more pressure in problems. Okay, so all these simulations assume curve, or in absolute rotation, Schwarzschild. Okay, charge does not need to be considered first approximation because charge is negligible. Astrophysical. Okay, so the current hypothesis states that every single black hole in the universe is curved. So we just need to put curve into our simulations and run simulations and start studying all this. Okay, but we are scientists, so we want to see if there are things beyond what is expected. What new things beyond a curve could be in the universe? There could be other types of black holes. In order to do it so, we have two ways. Either we run away from the hypothesis of the uniqueness theorems, for instance, adding hair into the game, so then you have higher black holes with additional battlefields, or you move away from general relativity to other theories of gravity, in which the curve theorems do not apply. So you can have as many new black holes as you wish. And there are plenty of them. But there are also objects that have no horizons. They are typically called black hole minicas, or horizontally compact objects, or ultra compact objects. There are many words. The fact is there is no horizon. Typically, it's assumed that there is no horizon, but there is photosphere to create these images. Okay, so an object can be compact enough in order to have photospheres, but not compact enough in order to have horizons. So they could exist. And I can advance you another thing. It's not even needed to have a photosphere to create a shadow. You can mimic this picture. Example, boson stars. Some kinds of boson stars. Okay? So the thing is, because we want to explore what this new field can tell us about the universe, so we want to study everything. We want to study all possibilities, all kinds of black holes, all kinds of horizontally compact objects, see what they have to tell us about observations, go to our instruments or go to our devices and check and see whether it fit or not, whether we can find observational discriminators or not. To this art of generating images of any compact object under any possible astrophysical scenario, and then go to compare with data. So here within us, we call it pseudography, which is a word has created to Diego Simon, invented it. And we use it for our own projects, and it's very successful work. Okay, this comes from cosmography. Some of you are aware of this thing. Not exactly the same thing, but more or less. Okay. So pseudography is the study of shadows in any possible scenario. But this is the challenge. Okay, we want to study images out of any sort of compact object via black hole. We don't care about this at this stage. The code is completely oblivious to the properties of the matter, of the gravity, and everything. We just need metrics. And when we have a line element, we can turn our code under any, not any, but under many scenarios of interest. So, theoretical background. This is very simple. For your view, you have taken a course on classical mechanics, right? All of you, right? So, this is the same thing. So, we start with a spherical symmetric line element. I will mention a little bit about rotation in minutes, but spherical symmetric line. So, typical shape with three functions. You know, in spherical symmetry, you can always redefine one function in terms of the other, using the coordinate. In this case, to remove the gxx component or make it equal to the dtt. Importantly, this can be done. I'm doing this because if you can see there is an r square of x. Why is this? We usually in spherical symmetry spacetimes we have minus a of r dt squared plus b of r squared plus r squared of the omega squared. And then not always you will be able to replace b in terms of a. For sure, you can, but other black holes, that's not guaranteed. Why I'm doing this? Because there are spherical symmetric objects like wormholes in which the radial function is not trivial. And then you can remove this r squared to x squared. So to have a larger flexibility, we keep this thing and work in general with this. Okay. So as I can say, you can always choose new systems of coordinates to remove the bx component in terms of a minus minus 1. Okay. So to have the gdt equal to indices down equal to y indices up. Okay, like in transit. But having in such a case a non-trivial behavior in the radial set. Okay, that's the approach. This is completely okay. So then you go and write the behavior of light rays. Light rays, general relativity, propagate around null geodesics of the background geometry. Two caveats. First of all, this is not true for nonlinear electrodynamics. For nonlinear electrodynamics, light does not propagate upon null geodesic of the background geometry, but along null geodesic of an effective geodesic driven by the nonlinearities of the field. This is important thing. Okay, this is many times overlooked in the literature when people do this kind of research. The second caveat is this principle is true in general relativity. If you move beyond general relativity, it depends on the theory of gravity. Physical principle can be followed or not. Okay, but we are in general relativity, so everything is fine. If you see this equation, It's something we all recognize. This is the behavior of a particle moving in a single effective potential, one dimension. Something we teach to our students in classical mechanics. So this equation, we know that there will be turning points. Points in which the particle approach to a minimum distance is deflected by the potential barrier and gets back to the server. But depending on the properties of the effective potential, there could be trajectories overcoming the effective potential barrier and getting into the object. This is the typical situation that you have. Okay, so this kind of behavior for the effective potential that goes to 0 to infinity, and then has a maximum, then there might have a minimum or not. For sure, there is not. For sure, there is a maximum, and then the potential goes to minus infinity and that equal to 0. But I'm depicting here for different alternative geometries within and outside general gravity. But this kind of behavior for the effective potential, a maximum going to 0 to infinity, and then going either to minus infinity or plus infinity is very common. It's a very common profile. Okay. The important point about this potential is the maximum, the existence of a maximum, because the maximum is called the photon sphere. Why is that? Because, as I said, for a photon that has an impact parameter below, let me see the equation. We'll call you the equation. In this equation, in classical mechanics, you have the energy here. Here you have instead the ratio between the angular momentum and the energy, which is called the impact parameter factor. It's the quantity of interest here. Okay. So for values of the impact parameter factor, actually below the one associated to this point, okay, because the impact parameter factor appears inverse. Okay. So larger values of the impact parameter factor means going down, the other way down. For values of the impact parameter factor above the one associated to this maximum, the photon gets to a minimum distance and is repelled by the potential barrier and gets back to you. On the other hand, if the impact factor is small enough, then you can get upper the maximum, and explore the internal region of the object. If the object is a black hole, and you find the event horizon before getting to any other any other point of the potential, then the photon is swallowed up by the black hole and you never see it again. Okay? Because of this, usually the shadow is assimilated with the maximum of the potential. Why? Because obviously, photons that go above the maximum are never going to be seen again, while photons below the maximum, they are going to be reflected back. So you get an image. So the shadow is associated with the maximum of the effective potential. Photons above, not seen again. Photons below, they produce an image. So the central brightness, the pressure in the image is associated in this interpretation with the shadow, with the maximum of the potential, which is the photon sphere. So photon sphere, maximum of the potential, and shadow become the same thing. In this interpretation. This is actually a canonical interpretation by Falke in his influential paper at the beginning of the century. Actually, starting with it, or again, with all this group of research about shadows. But we are going to see this is not. This is true. It is mathematical modeling because there is no disk here. As soon as you put this into the game, things change completely. Okay? We are just doing with equations mathematical point of view. Another important thing is that this maximum of the effective potential is unstable because it's a maximum, which means that a photon that has an impact parameter very close to the maximum can circulate several times around it in larger and larger orbits before getting to you. So a photon that has an impact parameter very close to the one of the maximum, to the critical impact factor parameter, can turn 1, 2, 3, or as many times as you wish before getting released yourself. Classical mechanics, they will be the circular orbits. Okay, here is interpreted as a photon that travels several times around. Okay, so in this point, the gravitational lensing is so large, the deflection angle is so large, it can be larger than pi. This explains why you can see the back of the black hole as opposed to a regular shadow where you only see the frontal part in this field, so you can see the back You can see the front, but circled several times by the black hole. Okay, so this means that the photon can turn many times around the black hole, provided that the impact parameter factor is very close to the one associated to the maximum. And this one associated to the maximum comes from the solution of these three equations that you find there. Imposing the first condition imposes that there is a turning point, and the other two conditions impose that it's a maximum. Okay, so these three conditions combined tells you what is the impact parameter factor. In the case of Schwarzschild, this is 3 square root of 3m, like 5.90 m. Okay, and the photosphere rotation, which is the value of r, depends also on the geometry you are considering. For Schwarzschild, this is 3m. It's very close to your equation. Okay, all good here with this classical mechanics problem. Just instead of talking about energies, we are talking about impact parameter factor. Okay, and instead of talking of particles or bodies, we're talking about light rays. Okay. As promised, things get really complicated, really mess up in the case of current. Okay, so there is not a single photosphere. Photosphere is completely spherical. The geometry is spherical. As soon as you get rotation, spherical symmetry is lost, it's broken, and then things get very messy. But there is an equivalent concept to the photosphere, understood as the surface of unstable null geodesics. Null geodesics that can circle several times around the black hole, but cannot linger there indefinitely. At some point, they are going to be either released to a asymptotic observer or either swallowed up by the black hole. Those swallowed up by the black hole, in this sense, are not of interest to us because we never see them. We are interested in the others here in this context. Okay, so this is the form into a surface which is called the photosphere. So basically, there is a region contained between two values of the radial distance and two values of the polar angle, in which there are null unstable orbits. Okay, so that's the kind of figure, the kind of image that you get. So there are two rays here, R minus, R plus. Okay, over here. If you turn the rotation to 0 or approach to 0, so these two radius are going to get closer until it merge into a single surface, which is the photon. Okay. So this, fortunately, this radii and this angle are known in a specific form. Why? This problem is solvable. Because when you run the equation of because this is a problem of perturbations. Okay. So when you perturb the Einstein equations for this problem, you get 4 equations, and only 3 constants. But it turns out, by a happy coincidence of the way general relativity works and the curve solution works, there is a 4 conserved quantity of motion, which is called the Carter's constant. So you have 4 equations in conserved quantities, meaning that the equations are integrable. They can be solved automatically. This is a happy property of general relativity that is not guaranteed to happen in other theories of gravity. That's one of the complications of trying to find modified black holes beyond general relativity. Okay, so for those of you that are familiar with this group, from the astrophysics group, they have people actually running the equation with these things, the numerical point of view. Okay, in the astrophysics group. Yes.
So I was thinking, the angular momentum of the orbits is not the concern, right? The
angular momentum of
the
photons around the black hole.
Yes.
Because they lose energy.
Exactly. So it doesn't need to be.
That's it.
But the
actually, if they didn't lose energy angular momentum, they didn't keep falling until the black hole. So there are mechanisms, the astrophysical flow that explain why the photon after some time start losing angular momentum and spiral inward the black hole. Otherwise, you don't have emission from that.
So this is the constant you lose from rotating to rotating, but in this case, the Carter one supplies the.
Yeah, separates the equation of motion. Okay. The equation, the integrals that you get are fairly complicated, but they are expressed in terms of special functions. Everything is under control. Okay, equations are much more complicated, but still within something that you can deal with. But as I tell you, going from spherical symmetry to rotation is, for theoreticians, is a bad game. Okay, so then you need to go up on the full power numerical. Okay, so if you don't want to do that, that's difficult. That's a difficult choice. Okay. Okay, so the next step that you do is, okay, we are talking about reflection points, photons that are turning around the black hole, because the reflection angle and so on. Okay, but how do exactly we characterize this? We with the geodesic equation. The same geodesic equation can be integrated for the deflection angle, this phi as a function of x. So this is a kind of equation. Generally, this equation cannot be integrated analytically, but we don't need to. Because we only need this equation for one purpose. Well, actually, it can be done in the strong field regime. These are the equations of both all these things to compute the deflection angle in the strong deflection limit. There is some kind of technique. If you read papers on gravitational lensing by individual photons, there is a technique allowing you to do this with this and get specific oscillators. Okay, but this is not the purpose of the talk. We don't need this. We can do it, but we don't need it because we are not interested in that. We are interested on knowing exactly for each photon with a specific impact parameter, what is this photon going to do with when circling around the black hole? Okay, because the impact parameter appears in the other deviation equation and the deflection equation. Okay, now obviously this black hole will be illuminated by the disk in all directions and also illuminated by the stars in all directions. And these light rays that are going to be deflected will go anywhere. But we don't care about these rays. We are not interested in these rays that come to us because we're interested in the image that we see. So instead of integrating this equation from the source to the final location, we do it backwards. We start with the light rays that arrive to our screen, integrate this equation in the opposite sense to backtrack the trajectories, to know exactly every photon from where exactly the photon came from. Okay, so for instance, this photon that arrives to my screen at this impact parameter value, I integrate this equation to track the trajectory and know exactly the location in the sky the photon came from. These trajectories will be for impact parameter values above the critical one, so it's deflected by the black hole, and these are below the critical one. So eventually, these photons intersect the horizon, to be seen again. Okay, so for those, this image, this is the black hole with the horizon, and this dotted black circle represents the photon sphere. Because the photon sphere is the location of unstable bound geodesics. So a photon like this that gets very close to the photon sphere can circle several times around the object. The closer you are to the photosphere, the more loops you do, the more half tours you take. Okay. In the exact case in which the impact parameter factor is equal to the critical one, the number of tours is infinite, formally. But in practical terms, this never will happen. It will happen never. This is unstable. Okay. So you might wonder at this point why we should worry about these trajectories like this one that intersected in the horizon. This trajectory you will never be seen in your screen because these trajectories should have originated from inside the black hole, which cannot be. Okay. The trick of this is that there will be an accretion disk here. And the accretion disk here can be inside the photosphere, part of it. So the disk can emit from inside the disk. So this trajectory before intersecting the horizon could intersect the disk, meaning that this trajectory could exist in your screen, could have been emitted by the part of the disk that is inside the photosphere, but not inside the horizon, obviously. Yes.
So when you talk about the shadow, you are also considering that the disk is there?
Yeah, the mathematical shadow is the one associated to the critical cube. From purely mathematical terms, it coincides with the photosphere, with the critical curve, with the critical interparameter.
The black lines.
Yeah, all the black lines. Yeah, but also the violet ones. Okay, actually the photosphere is in red, but only with two tones because you should have keep incorporating more and more of it, so going to the infinite number of loops. But obviously, we cannot be. I cut here the picture at two hollow orbits. Okay. Because there could be, for instance, this one that intersects the horizon, crosses the equatorial plane 1 and 2, so it turns more than 2 pi. So you say, okay, this trajectory will never be seen from my point of view. Not exactly, because there could be a disk here inside the photosphere emitting this light rays. So as soon as you get the accretion disk into the game, mathematical shadow is not a real shadow. It does not need to be the real shadow. Okay. Good question, because now I go to the disk. Until now, everything.
Disturbance. I have a question about previous slide. This figure is only valid for, I think, when we discuss the motion of photons. What happened when we discuss the motion of phonons, not photons? In the case of acoustic black hole, there is a problem when we divide this direct lensed and photon ring emissions. So how we can discuss in the motion of phonons in the case of acoustic black hole? So whether this question is still hold for this, or we can need to develop a modified version of the code. Sorry for the disturbance.
Yeah, it's because the sound is not that good, so I'm not sure if I got the question that you wanted to ask me.
Speaking about acoustic black holes.
Acoustic black holes.
Trajectories of photons.
Yeah, I know.
Something similar to this.
Yeah, I know little about
So
that.
my main question is that what happened when we discuss the motion of phonons, not photons?
In acoustic black holes, I mean, analog black hole models.
It's basically the same thing, but you get some dispersion. So the trajectories might not
Do you
be
have the
exactly
micro connected
geometric.
there?
Sorry?
Do you have the zoom connected? Because otherwise they cannot hear you.
The microphone.
Okay. Okay.
So for low wave numbers, something very similar to this. For high wave numbers, you get something like a rainbow metric, and
Okay. Okay, so let us go to the disk, because this is only geometry, nothing else. But now we need to make the disk. Okay. Typical pictorial representation of this and the image together with the image that I'm going to explain the details now. So black holes and potentially other ultra-compatibilities with the horizon are typically surrounded by accretion disk of the material or the companion star or captured material or whatever. It can be particles, it can be gas, it can be different sorts of matter that are infalling, losing energy and angular momentum as they get closer to the black hole because of the heat, because of friction, and then emit light. This light, this elemental radiation, is the main source of illumination of the black hole. Okay, so we don't care about what the stars in the illuminating the object are doing. We only care about the accretion disk. Okay, now the way this material falls into the black hole determines the optical, geometrical, and emission properties of the black hole. And this is very important because actually the modeling of the disk in terms of these three features is critical in the generation of images in combination with the background geometry you are taking. So I said there are three main ingredients for the generation of images. Optical properties, basically, whether the disk is transparent to its radiation or not. Transparent means after how much distance the photon emitted by the disk is going to be reabsorbed by the disk or not. This is important because for a strongly lensed trajectory that tend to travel several times around the black hole, so they take a very long path, they can be reabsorbed by the disk if the optical depth is too small. So you are never going to see those light rays that come from the back because they are reabsorbed by the disk. Furthermore, the disk can be transparent to its radiation or not, depending on the frequency you are observing. This can be a frequency-dependent feature. The second thing are the geometrical properties. So the disk can be anything between infinitesimally thin, infinite zero layer of matter, so under the black hole, can be a completely spherical bubble, or any shape in between, depending on what is happening in this process of infalling around the black hole. And the third thing is emission properties, how the disk emits, particularly with the distance, or with the EPA parameter factor, or with any other features of the disk. These quantities are related through what is called the radiative transfer equation, which takes this form. Basically, managed by the intensity, emissivity, absorption, and the photon's frequency appears here because, as I said, several of these properties can depend on the frequency of the photon, and do depend typically. Now, how this equation with so many free variables are solved? Again, general relativistic dynamic equations. If you read papers on this thing to see how they do it, they use a different pool of assumptions depending on the kind of disk they are interested to model and solve this equation numerically to get a relation between these variables. Okay? This is something very funny for astrophysicists, for those working in numerical relativity. It's not funny for us because we are theoreticians, at least myself and some others. So we don't want to get into this, at least at this stage. We want to do theoretical physics. We have new paradoxes. We have new theories of gravity. We want to test new things. We don't want to get into the messy world of astrophysics. We will do this stuff. Okay? Or if you think the other way around, we trust in astrophysicists to do their job and to supply us with reliable models of the disk. They are not exactly doing this because the field is very complex. So we have some uncertainties in the disk modeling that we have to live with them at the moment. So we're going to shortcut this thing to find ways out of doing our own research. It's a very complex field. Numerical relativity, a lot of human power, a lot of time for computations, highly demanding field. So we don't want to do this. I mean, we can do this, but then we lose track of our final goal, which is to test objects beyond general relativity predictions. Is there anything else that we can do? Fortunately, there is. This is good for us. There are some people out there in the world that has been compassionate enough to do the job for us. What they have been doing? They have thought the same thing as us. This is too complex, and I don't want to get into it. How do I do it? Okay, I get the results of the codes under different scenarios, and I try to see if I can find a family of profiles that more or less reproduces the same as the codes without doing the codes themselves. Kind of shortcut. And they have come with this proposal, which is called, is based on the standard amount Johnson distribution, a modification of it via this description of intensity profile. That depends on only 3 parameters. These 3 parameters are related to properties of the disk, geometric and properties of the disk. Adjusting these parameters, they are able to, more or less, reproduce with semi-analytical profiles the results of general relativity or GR-HD simulation without getting into a decimal simulation. And they have gone with this proposal. And there are several techniques dealing with this with hundreds of proposals according to different specifications of this. Yes.
This is true for standard model matter or also for other general matter theories?
Okay, there are no assumptions here about them. I mean, the only assumption is that this is general relativity.
But the
That's important.
magnetodynamics?
The magnetodynamics is inside general relativity. So they get the results of simulations inside general relativity.
Yeah.
See the results. And then there is any kind of profile I can do in my simulation without getting into simulation, but as we are going to tell you, with Mathematica to run my simulation and get to the same point. Yes, there is. With this thing.
Yes, no, my question is, has this been tested only for standard matter or also for modified matter?
The thing is that these things has nothing to do with, I mean, yeah. So you need to model the disk with some kind of matter, regular matter, dust, particles, whatever. Okay, so these simulations are always dealing with matter because it's regular matter regarding the things that are falling into the black hole. It's not about what the black hole is made of. It's a different thing. Okay, it's the matter that is surrounding. So this is regular matter. The trick here is that this is with general relativity. If you move this profile beyond general relativity, that's a different thing because you should need to run simulations, magnetodynamic simulations, in this new theory beyond general relativity, and then come up with a similar proposal for intensity profile. Problem with this is that running the simulations, we come back to the same problem that we have here, but further complicated. Because beyond general relativity, you don't even need to have exact analytical solution of rotating type. There are few in the literature. And even if you have them, you have to start anew with the whole process of running the equations to run the simulation. So that's a big trouble to do this thing. The same happened with gravitational waves, by the way. Okay, so they go with this thing and several parameters with that pre-rankas. And they go and propose hundreds of values of these parameters adapted to different scenarios coming from the numerical simulation, the numerical relativity simulation. Okay? But this is much simpler and is easy to implement in mathematics, as Gonzalo is going to tell you. Anyway, one main result of these simulations, which is very important for us, is that these simulations and general relativity magnetodynamic ones agree on something which is the following. The side of the disk, the geometrical side of the disk can be a bubble, can be some infinitely thin disk, or something in between. But these two strings of the spherical symmetric, infinitely thin, display completely different observational properties in terms of shadows and in terms of photon rings. This is important. And because typically this is an assumption in you do, the question is, nature is closer to which of these realities? In terms of the observables, because these will have some kind of thickness. So reasonable thickness from observations or for simulations, the predictions for the observables are going to be closer to the thin disk or to the spherical ones. Answer, to the thin disk. Actually, the predictions of the spherical symmetric models are only applied to those models. As long as the disk has some thickness, but is not completely spherical, do not apply. And this is very important. That's what I'm going to explain you when I discuss the observable. Okay? So we are not sure about the exact thickness, but we know from these simulations that the predictions in terms of observables are going to get conceptually closer to thin disks than to spherical disks. Okay? So for instance, these are the 10 profiles that we extracted from one of these papers. Okay? These profiles assume monochromatic emission in the frame of the disk, which is not exactly what we do in observations. Because observations we observe at fixed frequency in our detector. Okay, the frequency does not need to be the same in the disk and on our screen because gravitational capacity. Frequency is going to be different. These simulations assume that the frequency is the same in the disk. So we're one of the weak points of this analysis. But in the end, everything gets characterized in between intensity versus the radius. And because the radius is related in spherical symmetric models to the impact parameter value, you can resolve this graph as intensity versus impact parameter, which is very useful for the simulation. Okay? And the two main features of this simplified thing that you have here that influence the observables are the location of the peak, the maximum of the emission, and the decay with distance. This influences the two sets of observables, the photon rings and the shadows. Now, a bit of theory. How do we compute this? When there is no completely transparent in optical properties, so a photon can travel around the disk as many times as it wishes, the conservation of the flux by the unit volume tells you that the rate of intensity divided by the cube of the frequency must be conserved. So this is on the frame of the server, on the frame of the screen, and this is the frame of the meter, the frame of the disk. This has to be conserved. Now, if we define the redshift factor like the quotient between the observed intensity, the observed frequency, and the emitted frequency, in a spherical symmetric geometry, these two frequencies are very easily related via the GTP component, like this formula. Okay? So the observed frequency, the total observed frequency, is just an integration over the full spectrum of observed frequencies times the intensity at a given frequency. And because of this equation, that can be related with the emitted frequency via this factor, which is only the metric quantity. Yeah. I'm integrating, because this is monochromatic, in the emission of the in the meter, this integral is immediately done, and then you find that the observed intensity is the emitted intensity scaling with the square of the metric function. And everything is a function of R. And because R is a function of the impact parameter, everything is a function of the impact parameter, which is actually what you measure. Okay, so relation of the intensity in your screen is related to the intensity emitted, for instance, via the model before, just multiplied by this factor, the square. But there is another ingredient in the game. This will be true if photons were emitted from the disk with some lensing to us. So we just need to take this factor into account of the A square and get the total intensity in our screen as a function of the radius or as a function of the impact parameter. Point is, because the disk is transparent to its own radiation, photons can travel several times around the black hole before getting to you. So we must take this fact into account. We must take into account the fact that the photon can be emitted from the front of the disk, from the back, or from the front, traveling to have loops before getting to you, or as many loops as you want. So we have to add to all trajectories. So M here means the deflection angle divided by 2 pi. The crossing integral. Okay? So it labels the number of half turns around the black. Okay? So we have all contributions. Because otherwise, with this formula, I'm only taking into account these contributions coming from the front of the disk. This is what we call the direct emission. The emission that goes directly from the disk to us. While every other trajectories are called photon rings. Okay, because they come from the back or from the front after several times. And now this is going to correlate with observables, which is what I'm going to describe now. Actually, by the way, this is a very funny picture drawn by Luminate in 1963 by hand, beginning. Do you know the guy? He's alive still, right? It's very funny when he tells this story, right? About how the paper is very interesting. Can be readable perfectly today. It's modern size, but 50 years ago. You read the paper and you publish to the archive, you think it's today, right? So it's amazing. It's amazing to actually, you can even see here. So this is the direct emission over here. This is what I mean. I don't know if you can see. Here there is something. This is the bottom ring. So they wrong, I think. So this is.
Did you run simulations or how?
This is amazing. This is packing all trajectories.
I think you computed stuff and then draw the thing point by point.
Point by point, yes.
It's
amazing. You track every trajectory of this on the computer, or the limitation of the technology of the period, and then track the point on the screen and go. Amazing. Anyway, we have better computers now. We don't need to do this by hand. Okay. Bottom ring observables. Okay. So the thing is, as I was mentioning before, that there are two limits for the size of the disk: infinitesimally thin or spherically symmetric. Okay. In the spherically symmetric case, which is the vision of Heino Falking in his paper on 2001, all these trajectories that turn several times around the black hole converge into a single photon ring that such that the central brightness depression completely fills this region. So the shadow is the interior region to the photon ring, which is identified with the photon sphere, and there is a single photon ring. Okay, this is the vision that we have. Nowadays, or at least at current stage of the discussion, we know that this is not exactly true, because the disk is not completely spherical and has lost, and this spherical symmetry is lost. There are two new features that appear. First of the features is that the photon ring that you have is not a single photon ring. It's a collection of infinite photon rings. Every photon ring is associated to the number of half loops that the photon has traveled. So there is the direct emission from the disk to you. There is a first photon ring of photons emitted from the back of the disk to you. There is a second photon ring from those photons emitted from the front that travel a whole circle and get to you, and so on. Okay? So the photon ring is broken up into infinite series of rings, which are similar in character to each other. But they do not contribute equally to the image. Why is that? Because what happened, because remember that these photon rings are associated to the photon sphere, to the maximum of the potential. But the maximum potential is unstable. So we start with an orbit very close to the maximum potential, but slightly displaced. So we can get the geodesic equations, perturb, retain terms at first and second order, and integrate the equations to see what happens after a number of turnings of the photon around the black hole. And you get to this equation, that the location of the photon after n half turns have been carried out is the original location, meaning slightly displaced the photon sphere, times the exponential of the number of loops, times this factor gamma, which is a number. This number is known in exact form for spherical symmetric geometries and takes this form. For Schwarzschild, it means pi. The value is pi. So it means that the location after one half turn of the photon is going to be, for Schwarzschild, like exponential of pi, which is something like 22. Okay, so after half a turn, the photon is already very far away from the original location. Okay, but what does this mean? If I take the limit n going to infinity and divide the location of the photon ring n plus m divided by the location of the photon ring n minus 1, this is a universal prediction of your geometry. In the case of Schwarzschild, exponential of pi. In the case of geometry, depends on the value of this function. It's another universal prediction. It does not depend on the accretion flow. This number is called the Lyapunov index that appears in other concepts of physics. Okay, so in some sense, the Lyapunov index is a universal quantifier of the way space-time bends the geometry. Your black hole bends the geometry. Okay. Okay. These locations are associated with the location of photon rings, which are measurable, but even better, the intensities are measurable. And it turns out that the intensities follow the same rule, exactly the same rule. So this is also the exponential of the Lyapunov index. It means that if you have a photon ring, two photon rings, for instance, the n equal to 1 and equal to 2, and divide the ratio of the intensity of each another, you have this exponential of pi for Schwarzschild, and the exponential of something different for other geometry, for other black hole. This is extremely interesting. Means that if we are able to measure two photon rings, collect the total luminosity, and divide, we get this number. So we can see if this number fits with Schwarzschild or not. It's a way of killing models, okay? Because there could be models with two very similar Lyapunov indices. So they both survive, but other models will be killed. Problem with this will be true if the disks were emitting exactly with the same emission at all distances. Why is that? Because these two photon rings, n photon ring and n plus 1, on its path did not travel the same region of the disk because the radial distance is not the same. So they travel different regions of the disk. If the disks were completely homogeneous, all good. They see the same luminosity. But because the disk does not behave in that way, they don't see the same luminosity. So this is a useful theoretical prediction, but it cannot go alone. It must come in combination with the properties of this. And that's where the problem lies. Because the modeling of the disk is not well known. Okay? So we have to live with this at the moment. Anyway, the n equal to 0 ring is what the Event Horizon Telescope, the device producing the images I showed you in the first slide, they measure the direct emission, contrary to what is usually popularized. That when you see a typical news, black hole with its photon ring, that's not true. That's the direct emission. The photon ring is somewhere over there, hidden in the emission, because it's very difficult to observe. Actually, it does not need to be separated by the direct emission. It can be inside the direct emission as an extra boost of luminosity. I recall a Lyapunov index, exponential of pi, 23 times the luminosity. Very difficult to observe. So the n equal to 0 is what the Event Horizon measures. Does not measure the photon ring, which is a shame because that's where interesting things are. Because of this, they are upgrading, not upgrading, actually building a new telescope, which is the next generation Event Horizon telescope. Within the field, it's called very large baseline interferometer. It's a very large interferometers, not physically, but virtual telescopes. Okay, that's actually what the HT does too. Okay, but just much larger scale and much improved sensitivity. Okay, so they are designing this thing. I said somewhere 20, 30 plus, probably much larger, but they are on it. There are some papers explaining the literature explaining the. Even for my Spanish collaborator, some Spanish that are in this collaboration, explaining how exactly this thing is going to expect to work. Okay, more things. Now we go to the sound observables. So what the size or what the central brightness depression has to tell us. This will be the naive expectation that you have. There is a black hole, but the size of the black hole is not determined by the horizon. The size of the black hole is not determined by the size of the photon sphere because these two images do not take into account the bending of light. this is the actual shadow. Because this takes into account depending on like photons emitted at the photosphere will suffer lensing and get to a server. This is the critical impact parameter value. Now, if this were purely mathematical black holes, this would be the actual shadow that you will see, the size of the shadow. But this is not true because it's not taking into account the behavior of the disk. Okay. Anyway, there is something which is called the inner shadow, okay, which is suppose that there is an disk that extends all the way down from the photosphere to the event horizon. So the very last particle of matter near the event horizon that emitted the light ray that get to your screen, that will have a size smaller than this one, that's the closer photon you can see near the event horizon. So this is a minimum bound for the size of the shadow, which is called the inner shadow. In the case of Schwarzschild, I think it's 2.9, something like that, 2.9 m. Compared with this number, which is 5.19, so this is a strong reduction. So this is a mathematical shadow, but the actual shadow can be reduced much further until the inner shadow has a maximum theoretical limit. The actual shadow, I mean, the actual size of this delta parameter depression depends on the combination of the background geometry, which determines what is the critical impact parameter value, and the properties of the disk. Okay. Now, there is another problem with this, which is the resolution of the measurement, which is by the H. They cannot detect, they say, brightness below 10% of the peak luminosity. So the peak luminosity they detect, below the 10% of that, they detect 0. Okay? So the size of the shadow they can determine has this bias already built in it. Okay? So one has to be careful when taking these things that they state at face value. Okay? There are several caveats here. Anyway, they claim that the size of the direct emission, which is observable, is a proxy of the shadow ratios, which is not observable. Because in order to do this, you should be able to detect those photons emitted near the event horizon, which is something they cannot do because of this feature. Okay, because obviously resolution is going to be always limited. So they go up, anyway, they go and throw this result into the game, and they claim that the size of the shadow is determined using these constraints. This is for 1 sigma, this is for 2 sigma. Okay? As I said, there are several caveats. First, that there is sufficient flux getting to the image. They assume a thick enough disk. There are some calibration factors that they put mathematically into the game in order to account for observational experimental mistakes and even theoretical mistakes. But even further, they assume curve as the solution. So by default. Now, if you have a black hole beyond general relativity, this assumption is overruled. So there are many hidden assumptions here. So this kind of also has to be taken very carefully. Anyway, in this paper of last year, so this 1 year is 200 and something citations already. Okay, because basically they get something like 60 alternative models to care, from modified black holes with hairs, modified black hole general relativity, horizontally compact objects, wormholes, all kind of stuff, and they put these objects to test. To test what? Use this observation because this is a theoretical prediction to test the parameters, to constrain the parameters of your model. So if your parameter predicts a shadow which is too small as compared to the result, they claim that this theory is ruled out or at least under problem. Okay, just to show you a little bit of the possibilities that we have here.
But from what you were saying, the results are incorrect, right?
There are several assumptions here, some explicit and some implicit. Yeah.
Well, I mean, but I'm
claiming that. No, they are not claiming that. They are claiming that the result can be trusted because of reasons.
Okay, so at least they discuss.
They discussed the thing. But subsequently, there are people that have been discussing this thing. Sometimes, okay. So some of you that are connected, your supervisors are doing this thing. So I leave it to you to the person you should trust. But this is open to discussion. This is quite new stuff. Okay, so it's just to show you the possibility.
But what they were doing basically is to say, let's say, testing. It will be parallel to testing modified gravity theory with the gravitational wave template that we have from here.
Yeah, something.
Kind of thing.
So the
Contrasting them.
thing is, you can measure direct emission, but you cannot measure photon emission with this technology. But there is a connection between these two things, between the direct emission and the photon ring emission from theoretical stuff. Because the photon ring emission at some point gives rise to the shadow after a few loops. And the shadow is a prediction of the theory, so they combine these things to say that what we observe is a proxy. It's a tell us more or less what is the size of the shadow in your model. So if your model predicts a size of the shadow significantly smaller than that, so it's all out. That's the core of the argument. But there are several things, several assumptions there that have to take into account. In particular, they assume care as a default thing. They are aware of that fact, but they dismiss it that this is not that important. I leave it to you to decide about that. Okay, so you can generalize all this stuff to any object of this you want. For instance, horizontal compound objects. So the point with this is that black holes, no matter what they are made of or where they are originated up, they have several things, several properties. Photon sphere, horizon, that's it. Depending where the horizon is, depending where the photon sphere is, you have different things. But qualitatively, everything is the same. It's not the same with these objects. Because every of these objects is different in nature, having photospheres or not, having two sizes or not, having different internal region or not. So the kind of image you can expect is completely different, varies a lot from object to object, which makes them easier to be rolled out with mechanical observations. At the same time, offers you new possibilities. But you can do the same thing. You can do a ray tracing and then do the same stuff that you do with black hole images. Okay? So this is for an object with two photospheres. There are many of them in the literature. But as I said, in observations, predictions for observations, there are qualitatively new predictions of this object. So on the one hand, it makes them difficult to pass pattern tests. On the other hand, they predict qualitatively new signatures that do not appear in black holes. For instance, imagine that you have the perfect theory of quantum gravity. You have solved all the problems of quantum normalizability and all this stuff. You go to your predictions of your theory to test your theory of gravity. And your predictions are the same that Yar predicts. Not the same, but the difference are qualitatively, quantitatively so small you cannot measure them. So you cannot know if your black hole is, your theory is real or not. You cannot test against the relativity. With this object, you can test. If your favorite theory of gravity or favorite theory of the matter field predicts one of these objects, like for instance, boson stars, perfectly reasonable object, so you can test this thing. If the thing has a single photon sphere, more or less is going to display similar features as a black hole. If it has different things like two photon spheres or two sides or internal region that can reflect parallel radiation, things are going to be very difficult, very different. But as I advanced before, even if you don't have a photon sphere, you can tune your objects or the parameter of your objects to mimic a shadow. So there will be radiation from inside the object, but this radiation can be so weak that it's not detected. So you, in your image, there is a central Tarmex region mimicking a shadow. Okay, just to make the link with the codes that Gonzalo and Joao are going to explain later, I just wanted to make you a few hints about this thing. Okay, so why we need a code? Because we need to put something. We need to make simulations putting something, and this something is related to you need a background geometry, obviously. Your favorite theory of gravity, your favorite theory of matter fields, or not. I just want to play with mathematics and put a line element. Okay, I have this thing. I need to assume a geometry of this. Geometry, spherical symmetry, infinitesimal thing, or get something else. I need to make assumptions about the emission. I'm going to put opacity or not to cut lengths. I'm going to select frequencies or not. What kind of profile I'm going to choose depends. I can use these SU profiles or something different. I might consider upgrading my things to full rotation, but as I said, this has a minor influence in images for detecting what we are going to detect, which are traces of new physics. And you can incline the images. We usually the line of sight observer as compared to the emission has no need to be face on. It can be inclined. Actually, this is what happens for an 87, which is inclined at 60 degrees. And you need to put this into a code, because this cannot be done manually. We are not illuminating any longer. So we need to do a code. Yeah. So there are several. Probably this is the Otto is the most popular one, developed in Paris, AIP Institute. There is a new one 2 years ago of R and your own, our own of a code. What are the output of your code? This direct emission always, like rays that come directly from the object to us. If we assume that this to be optically thin with some optical duct, we are going to see photon rays. See, if the inflow is spherically symmetric, there is only a single photon ray. But this scenario is disfavored at current in the literature. If it is not completely spherical, you are not going to see a single photon ray, but several. And the location, the thickness, the diameter, and the luminosity, they correlate with theoretical prediction. To some extent, they correlate with observable things. And the same happened with the central variable image. Just to show you a few images. Well, first, the code. Well, this Gonzalo will be explaining. It was developed by Gonzalo. I upgraded, you have upgraded much more. There are multiple available versions. So some of them will be able to, any one of you to peer into it and to use it. So immediately workable. Just change the line element and run the code, single extraction, and let it. Then the magic begins and let the code produce your images with all the observables they do. So this is what the code does. Ray tracing, classification trajectories. We can deal with any spherical symmetric geometry as long as the thin disk is present. No matter providing this frame, I will already talk about this thing. We can deal with horizontally compact objects, different kinds of them. We can already tabulate the solutions for boson stars to orbital inclination, applying the disk as many ways. And there are some improvements, it can be improved to be more efficient in terms of time. There are some things that can still be upgraded. So many of these things were not developed on the first thing, the first version. The first version was only the ray tracing, was already complicated enough. All these features were built up before. After. And then we have other things that we can do. It's not still included in the disk, but at some point, maybe with the help of you or you independently, you will be able to do this. So this is what typically the code produces in terms of images. It also releases as output numbers related to the location, thickness, intensities, all these things. Okay, so these are the typical images. So these are for 4 of the models that were presented before, the SQ2 models. So these 4 plots are the intensities. For instance, in this one, you are cutting the integration at the second photon ray, n equal to 2. So we need to serve the direct emission, the first photon ray, and the second. This is the direct emission, this is the first photon ray, this is the second. Okay? Depending on how separated they are, you are going to be able to see it in the full images or not. For instance, here you can see it. But there is something like 2 photon rays separated. Okay? The same happens here, the same happens here. Actually, the photon ray does not need to be inside the direct emission. It can be outside. Depends on the geometry and depends on the disk. So in this case, the photon ring is inside. It's over here. You cannot see it, but I can assure you it's there. This will be the first photon ring and second photon ring. This is the first photon ring. It's immersed into the image. You can see it here. So this will be a disk that extends to very far away distances. So all this thing is direct emission. Then you see a boost in luminosity, which is the photon ring here. And then there is a minor boost of luminosity associated with this thing. As you can see, with the same geometry, which is this is Schwarzschild, depending on the sensor of the disk, you get 3 different images. So this is why it's a messy field. It's very entangled. Geometry with this. Okay? And there are already assumptions here in these images. Okay? We can do numbers. We can compute the Lyapunov exponent. Remember, the Lyapunov exponent is an universal quantifier in the n going to infinity. At the particle terms, we don't know until infinity. The photon rings. So let us keep at the first and second photon ring, which at some point in the future we'll be able to measure. So we can compute this radial luminosity and see to which extent it follows the prediction of the Lyapunov index that only depends on the theory. on the gravitational field, on the gravitational configuration. For Schwarzschild, this Lyapunov exponent for these two photon lengths, this is valid. This means that if we are be able to measure the luminosity at the first or the second length and make the ratio, I should be able to measure this number. If the disks were completely homogeneous in emission, because this is not true, the actual number that I'm going to measure will depend on the assumption of the disk. So this is what happens. This is the actual numbers for different emission models. As you can see, these models, there are some models that are grossly overestimated the Lyapunov index. Okay. So these three models. There are others that are underestimated, and there are others like these, that more or less the same thing. Okay? Meaning, if we have a good control upon the properties of this, if we have a good model on how the disk emits in this particular scenario, and we in the future are able to measure two photon lengths and start that number, we can compare that number with the actual number of my theory of my object. So it's a kind of test that does not confirm your object, your geometry. I can't go out. Right? That's why this is such an important thing to be able to measure in the future. Okay, so just wrapping up all the analytical things that we do. Okay, so these are numerical, but it's numerical in the sense of mathematical. Okay, it's very easy to use. You don't need to start making codes. But does this talk of what I was doing? So theoretical concepts have been introducing critical, pure photon cells, adversarial. These are theoretical concepts. Only depend on the background geometry. Has nothing to do with the disk. As soon as you put the disk into the game, problems, because we don't have a good control upon that, and we need to go to numerical simulations. The numerical simulations are dependent on the choice of the parameter, which is model dependent. Okay. So that's a problem because two black holes can be extremely similar in the direct emission. They can have two black holes with different properties in terms of horizons. Can be very similar in the direct emission, but deviate strongly in the features of the photon disk. Why? Because photons on the photon disk are very sensitive to the specific details of the photon sphere. So two photon spheres that are moderately different to different black holes will produce photon disks that are very different, but direct emissions that are very similar. That's the key. That's why it's so important to upgrade technology to go to these two things, to separate these things. Other effects have to be included. And this is very active. People are discovering all the time new effects that are not taken into account. So this thing, the time delay in illumination, something that I basically found in a paper. I never thought about this. It's basically the photons that get close to the horizon because they take a long time because time delay to get to you. The matter is flowing. So actually, you have to take this effect into account, and this is not taking into account. So the conclusion is that when testing rather than something regime, the existence of other objects, the cosmic zoo, is something that we have an opportunity to do. I include here a summary of critical concepts. Okay, just for your perusal. But before discussing this, just let me tell you that we started these things, the notebooks, in an organized way because we plan to publish a book. It's more or less written at 90%. 90. The remaining 10 is because the guys of the notebooks had to supply this. So we started saying, okay, let's write a book with basic and advanced black hole physics, but something useful. Meaning something that we do in a regular day basis. What do we do on a regular day basis? Run Mathematica for everything. For tensor computations, for numerical calculations, for shadows. So I said, let us organize these notebooks in a good way to be included here, to be useful. So the next thing is, okay, so we can do a course for this. Since we are spending some time on this. So at some point next year, this will be released, including this kind of mathematical notebooks for shadows, but also for many other stuff. Okay. And so I use this slide with the general concept. So you can follow up now how all these things that I have been talking about, how they go into the notebooks to do this thing. I can promise you, because knowing the two guys that follow me, that this is going to be very good. Because I have seen how they work. And because Gonzalo spent 2 weeks without seeing his kids in order to develop the code, I think it's worth the effort, because it's really, to me, it's really amazing that Mathematica can do this in reasonable time to produce this image. Okay?
So what time scales are we talking about?
Depends on the resolution that you want to achieve. So how clear you want the photon lens to be seen. Depends also on the shape of the geometry. If it is Schwarzschild and you want to see, like, because these are iterations of, it's like 10,000 photons, for instance, something like this, it takes how much? 1 hour or something.
Wow.
Yeah. So what we do is to start simulate with few photons, okay, to see what is happening, and then for the final images, we leave the computer.
1 hour on any typical computer or on a cluster?
It's just to feed it, because there are several ways to feed the data. You need to create first the data of the photos, and once you have the data of the photos, generating the images is matter of minutes. Okay, so that's how it works. In this one implementation, probably in the implementation that Joao is doing, he's doing a different stuff. Okay, so he will explain. Okay, but this now, if your metric functions are containing elliptic integrals or hyperbolic functions or whatever, it's longer. So still within hours. For images that can be presented in math. Before that, when doing research, is less than 1 hour. Okay.
Okay, let's have time for some questions or comments here in the room. Yeah.
Hi, thank you for this nice talk. I would like to ask you if is it so, because here the whole topic is about intensities, right? And
yes.
Intensity profile.
Yeah.
Can one expect to, at least in the future, try to measure some polarization patterns from the right, or this is out of?
It's not in our top priority list. We have other things first to tackle that is not included here. So we are solving problems one by one, increasing difficulty or increasing relevance to us. So first of all, this is for thin disk. We would like to introduce some thickness. That's complicated already.
But the event file does it provide also information about this?
No, it doesn't tell you anything about that. You need to go to the papers forming the core of the numerical stuff about what kind of assumptions you do. There are papers about this, so they are based on that. They assume these models and then to interpret the data according to this. Actually, depending. There are 2 papers, theory and astrophysics, for us are the interesting ones. So it's very well thought already. But it's based on the previous analysis. But this is very fast evolving. Okay, so every year we get new papers teaching us things that were not before. Okay, it's actually from that point of view, it's not that well developed a gravitational wave area. Okay, you will think that everything is already developed in theory. That's not true. There are many discussions still going to and fro about how exactly integrate these things.
So, do you know what energies do the photon achieve while spinning in this?
No, I have no numbers now.
So what I was thinking, and it's connected to the question I was asking before, is that they could be sensitive to linear interactions among themselves.
Yes.
They are predicted already in quantum electrodynamics.
Yeah, I know what you mean.
So
particularly because there are highly magnetized fields around the black hole.
And there's a lot of intensity of light. So it's a very small effect in quantum electrodynamics, but that would make basically the propagation non-coalescing.
To be effective. Yeah.
And that would be a mess, right? I guess for all of this, or maybe not, or maybe it can be
no, actually
in the type of fluid, or.
I mean, if you modify the equation of Jeter's in motion to take these effects into account, from a theoretical point, it's easy. I mean, getting the code and implementing that feature of the propagation has no problem. The problem is that you incorporate another unknown variable in the game, which is exactly how this information are going to take place, and you already have too many dependent variables making interplay to generate images. Okay, so that's another complication. I mean, it's true. I agree with you. I've been working on this, but putting that into the game is making more variables.
Maybe it would be interesting to use, because in quantum electrodynamics, there is no freedom, there is no extra parameter, you have a
That's true.
value, right? So maybe playing with this and seeing if there is any difference could be interesting, because we know that interaction is there. It's been measured in the LHC.
Yeah, I mean, getting the effective Lagrange at first order. Put in there, plug in the right numbers and see what it is.
Exactly. I don't know if something will change, but if it will.
I mean, Euler-Heisenberg has been, the images have been studied.
Okay.
I don't know if the right numbers have been included there. Comparing this number with intensity, I don't know. Usually the extra parameter are taken as a free parameter.
Yeah.
You compare energies, I don't remember, but maybe.
Okay.
But that way, from the theoretical point of view, it's okay. But from the point of observation, it's at the end because you already have too many. Many variables that are playing against each other. So just putting another one again. So.
Okay, so we have time for a short question online. If not, we will close the session.